So Professor Isao Tanaka indeed does not need any introduction. Anyone can type in Google and see all his CV and activity, many papers, and many innovators and others. So I want just to say, Isao, thank you very much for coming and joining us, for all you have done for us. We are very honored to have you here with us. Now I want to kindly invite you to the stage to begin your talk. Please come.
Thank you very much for a very kind introduction. And I feel very much honored to have an opportunity to give a talk and a lecture in this very prestigious institute. And I am Isao Tanaka, as introduced. And well, probably I made one slide to introduce myself. So I came from Kyoto, and this is Japan. Probably most of you know Tokyo. And Tokyo and Kyoto are very confusing, but Kyoto is an old capital. It's 500 kilometers away from Tokyo. And I have been in Kyoto University for a long time, and also I was in Stuttgart in 1992 in Germany. I've been working on material science. I'm going to talk about theoretical calculation and data science issue, but I was grown up or educated as a material scientist, and I did many ceramics experiments and also metals experiments. So experiments, synthesis, spectroscopy were my major subject in some years before. I have been working on the first principles calculation, electron and phonon, that I will give in this presentation. The research insights are quite broad, all fundamentals of material science, and recently I'm very much interested in material discovery. This is my interest. Okay, so the subject of this series of lecture is the scientific discovery. This is a book published in 2009 by Jim Gray, who unfortunately passed away. And he mentioned that experimental, theoretical, and computational sciences are all being affected by data diffuse, and the fourth data-intensive science paradigm is emerging. He somehow mentioned or predicted this in the year 2009 or 2007. And actually, we are witnessing the emergence of that fourth paradigm. The new era of data-centric material science is going on. Well, I think in everyday life you have experienced that data-driven technology or science is very much useful for sometimes unnecessary changing your life. And there's always some data. If you play with your PC or play with your cell phone, there's always some data. And the data is stacked by somebody, some big company in the United States. They over all the data and they control our life. It is sometimes not comfortable, but we use it. But in the case of material science, the data, well, algorithm is already there. They have many different kinds of algorithms. But for the data, we do not have much data. Well, if we think of data, there are several kinds of data. One is database of experimental result. Sometimes some people use crystal structure database, which was established in Germany, which is called ICSD. Well, I'm talking about inorganic materials. And there are some different cases for the organic molecules and so on, which is not my field. And the story is a little different. So please allow me to speak only on inorganic materials. But this is inorganic crystal structure database. The other one, ICDD, is often used for the analysis of powder diffraction. And some physical property data are available. This is also a German product. And it was called Landau-Bernstein. And there are a lot of books for databases. But these days, it is accumulated and transformed into the Springer. So if you have an access, you have many different kinds of data. But unfortunately, the data for some specific properties are quite limited. For example, for some electric properties, there are sometimes only 100 or a few hundreds of registries, not like millions or billions of data. So this is the situation for the experimental database. Going to the first principles database, these days, first principles database becomes more and more well-made. One of the examples is the material project. This is established and still going on by the Californian group in the United States, and this is freely available, so everybody can log into that project and you can use it. There are some other databases. NOMAD is the European one, and the NADI is the Japanese one. All the databases are available for everyone. So the first principles calculation is a topic I'm going to talk here, because with first principles calculation, we can get material data quite efficiently and with the same quality. So, of course, we need some experimental database, but in parallel to that, first principle data becomes more and more important. The third one is the experimental database, possibly made by automated experiments. Sometimes robots produce a lot of data, and that can automatically transfer into the database, which can be used. But still, it is a kind of stage of dream. And many people are trying to establish that type of experimental facilities, but most of them are not in a public domain. They accumulated the data, and still they use as an in-house database. But well, we means everybody in this field are going toward the direction to have the public database and also make it for the common use. But today, especially the first part of my talk, today, first one and second one, I will talk for the first principles calculation. What we can do, what kind of information we can learn by first principles calculation. So, well, I designed this talk mainly for the student, including undergraduates, so probably for the experienced researcher it is somehow boring. But let me explain what is the first principles calculation from the very beginning. First principles calculation sounds a little bit strange for the person who heard this for the first time. The first principle means starting from the principle of something. In this case, starting from quantum mechanics. So this is a non-empirical description of structures and property of materials. often based on density functional theory. It's not necessary, but density functional theory is quite useful and efficient for performing quantum mechanical calculation. And the most important thing is that it has predictive capability of crystal structure and property, spectra, etc. Without any knowledge of experimental data, calculation can't predict. This is different from other type of calculation. Other type means the opposite to the first principles calculation. The computation method based on the physical quantity and empirical laws. For example, if you know some property of some steel and some elastic properties or some strength, hardness, etc., then you can compute, you can model some of the complicated structure. But that is empirical type of calculation. It is not a prediction or predictive capability shown here. But a known experiment that for this calculation, we do not need any of the input as a data. Okay, so this is a kind of history or progress of first principles calculation. Here, 1980, when I started somehow the research. And well, at that time, first principles calculation can handle only very small crystal, simple crystal at zero temperature. And this was used only for the fundamental issues in physics. And, well, but the progress of computer hardware and software is remarkable in these 30, 40 years. So gradually, the possibility to compute larger crystal becomes possible. And from the year something like 2000, we were able to compute some of the complex defects or nano crystals. And then that is the time for the material science, from the fundamental physics, solid state physics to the material science. Because in material science, we have to have many different type of nanostructures or defects. The surface interfaces, of course, take a very important role for many properties. And also, from those years, it becomes possible to compute phonon using first principles calculation. That really is the topics of the second part of today's lecture. And by computing phonon, we can now obtain the finite temperature properties for structure. Up to here, it was only at 0 Kelvin. And the first principles people are always criticize that by experimenters that all the properties are at higher temperatures or room temperature are at 0 Kelvin. But actually, even the 0 Kelvin calculation is quite useful. But well, without that kind of capability of finite temperature properties, it was just a kind of excuse. And again, with the progress of the computers, it becomes possible to perform massive calculation and register that as a database. So I will show some examples to handle millions of different crystals registered in a database, which is not possible to be performed by experiment. And those data can be used for the material informatics to discover some new material, which is the topics of this today's seminar workshop. Okay, if you are interested in first principles calculation, there are a number of computational codes available. But they are well established, and I should say similar quality. But depending on the software, there are some pros and cons. They are different in the basis function, and they are different in treatment of electrons, and also price are different. Those files codes are freely available, so everyone can access to that and download that, and immediately you can use it. And some other code you need to pay somehow, a small fee or large fee depending on the software. But of course, there is no free lunch. If you use free software, it is sometimes difficult to be used. If you have sufficient knowledge or skill, then go ahead and use the freely available code. And we are using this BASP code. This is quite balanced and quite useful. And most of my talk today is based on this BASP code. Here I show plane wave, and here pseudo potential PAW. I'm going to explain what is that. This is some kind of the ideas you can find in quantum mechanics textbook. If there is multi-electron atoms here, the potential is shown like this. This is the electrostatic potential around these atoms. And the wave functions are something like this. It shows some kind of vibration near the atom center because of this very deep electrostatic potential. And if we want to compute this wave function as a Fourier series at the Fourier mode, it is quite time-consuming or very expensive to expand this type of oscillating wave function. Instead of that, we use this type of pseudo potential, which avoid the infinitive, the small potential at atomic center. So with this, we were able to have this non-oscillating wave function. This is called wave function, which we compute. This kind of pseudo potential, pseudo wave function idea was not new. It was already proposed in 1950s or 1960s. But these days, we can make this type of pseudo wave function or pseudo potential without any knowledge. It's automatically made, and also it is possible to transfer to the different system. For example, silicon metal, silicon 4+ with the same pseudo potential. In that way, the computation becomes so easy and also reliable. So this is a technique which is used by most of the computation code I have shown before. So pseudo potential PAW is something similar, and plane waves are very often used. Okay, here is some flowchart of first principles calculation. You need to have some kind of input what you compute. And it is not necessarily the final structure, but you need to have some kind of input. Like in the case of SiO2, you need to specify how many atoms in the unit cell and which is a space group. Space group can be changed afterwards, but you have to specify at the very beginning a kind of space group. And initial lattice parameters, and also chemical element initial position itself. I said initial positions because those positions or lattice parameters can be optimized finally by doing first principles calculation, and as output you can add some electric magnetic structures and also total energy, force on each atom, stress tensor pressure. if this is a final structure and a stable structure, you may not find any forces acting on atom. If there is a residual stress or residual force on some atom, it means it is not at the ground state. So we move that atom according to the force or residual stress, and the structure are optimized. So in an iterative way, the structures are optimized, which can provide this type of structures with unit cell by unit cell and optimized atomic position. Let me show this as an example of H2O. This is some kind of guessed structure, initial structure as an input. As I mentioned, after calculation, you can end up with this type of forces, residual forces. According to this force, we move the atom toward that direction, and some iterative calculation is performed to find out this is the most stable structure without any residual stress. Then we also optimize this unit cell dimension to make this residual stress to be 0. Then you can find out the unit cell parameters, lattice parameters. So this is optimal structure as an output. Previously, probably up to the year 2000, or some, 2000 or something, the structure optimization was not efficiently possible. But there was an idea for structure optimization. It is very simple to make this. But numerically, the accuracy was not good enough. Only these 20 years, the structure optimization becomes quite routine, and everybody can do that without much knowledge. So now we can do this quite routine. So this is a kind of electric structure. I think you often find in some journal articles or textbook, wherever. This is for BCC sodium, which is very simple. And this is so-called band structure for the energy dispersion. So here is the Fermi energy up to this energy, and you have all the levels are filled. This is rather complicated, and at the first look, it is difficult to interpret. But actually, this is a geometric net with this first previous zone, and this blue arrow corresponds to the wave vector from gamma point to H point, which corresponds to the gamma point to H point in the first previous zone. And this red one corresponds to here, and the green one corresponds to there. In that way, we plot the energy as a function of wave vector. This you learn in elementary solid-state physics. But actually, this type of electron structure is not always useful. And well, for some specific consideration, this is very useful, but not always. We look at more frequently this density of state. Density of state is where the electrons are located, which density at each energy are found. So in the case of BCC sodium, this is very typical near-free electron material. So the density shape of density of state is something like parabola. So this is in agreement with the near-free electron model. In that way, the electronic structure can be discussed. Another one is a real space charge distribution. This is the charge distribution in comparison between diamond and graphite. You know that both of them are just carbon. But if you plot charge distribution, you can find this covalent bond between two atoms. The electrons are really covalent here, the 4 bonds. This is the case of graphite. You can find that again, covalent bond, 3 covalent bonds from the one central carbon atom. And many people think that diamond is very hard. Graphite is soft. Actually, graphite is used for in a pencil, but it is true that it is soft. But actually, graphite is not so soft. If you look at this in-plane bonding, this is very strong bonding, which is much more stronger than the bonding here. That is the reason why you can use carbon nanotube for some structure application. This is very much used for very high strength structure application, because they can use this very strong covalent bond and not using this interplanar, very weak van der Waals bonding. So this type of information can be obtained by the real space charge distribution. But this is again the one structure of diamond, and the diamond is from the transparency you can guess that it is iterated. So you can find here a band gap, clear band gap. But in the case of graphite, it is electrically conductive, so there is no band gap. Actually, the S of state here is very small, but it is finite. So it has electric conductivity. Also, by the first principles calculation, you can obtain many different properties. For silicon, if you compare diamond, equilibrium volume is here. This is the volume versus the total energy. So if you make structure optimization, you can end up with the volume here. But also, by changing the volume, you can have this type of curve. If you also perform calculation for beta tin type, which is a higher energy structure of silicon, you can have another this type of curve on volume versus energy curve as shown here. And if you make the common tangent of these two curves, it corresponds to the slope of common tangent corresponds to the phase transformation pressure. Because at this pressure, the enthalpy becomes the same between these two phases. So it corresponds to 12 GPa by theoretical calculation. And it is the same by the first principles calculation. So first principles calculation can accurately predict where at which pressure the phase transformation takes place. And it is in good agreement with the experiment. From the curvature here, it corresponds to the bulk modulus. The bulk modulus is somehow very rough measure of the hardness. Hardness is a very complicated property, but you can guess the hardness if it is hard or soft just by computing this bulk modulus. It is very easy to compute. So in that way, you can accumulate many different kinds of data. For those handling materials. Of course, you're not handling unary materials or elemental metals. Rather than that, you handle compound. In the case of compound, of course, the most important quantity is the formation energy of compound. In elementary thermodynamics textbook, you always find this type of equation. The formation, give the energy of the formation is the most important quantity if it goes to that direction or not. The standard gives free energy of formation in thermodynamics is expressed with this equation with the chemical potential as standard state shown here. And the standard state means this A is not atomic element A, but it is, if it is aluminum, it corresponds to the aluminum metal. If it is oxygen, then it corresponds to the O2 gas. It is a standard state, often used in chemical thermodynamics. So in that way, experimentally people can define the formation, gives energy of formation. By first principles calculation, we can do in the same way. We can just subtract the total energy of these substances with total energy of substance A and B. By that, we can obtain the energy of formation at 0 temperature. Of course, this is different from the thermodynamics, which is often used at 298 Kelvin or 25 degrees C. But other than temperature, the equation is somehow similar. And actually, in most of the material, the temperature effect is not that much between 0 temperature and 298 degree Kelvin. So anyway, we can use this to measure the formation energy of this compound. One example. This is a lithium battery, which is often used in our daily life. And this is the battery voltage is obtained by this reaction. Lithium iron phosphate compared to the simple iron phosphate and lithium metal. Sometimes this lithium metal is inserted into carbon materials or some other anode materials. Anyway, to make the story simple, I take this here, lithium. Then performing all these calculations for the by PAW method, you can obtain these energies, and by subtraction, you can find that the energy difference here is 3.45 electron volt. In the experiment, if you construct this type of lithium battery, and the electromotive force is expressed like this, and putting the Faraday constant, then experimentally, for this reaction, it is 3.4 volt. So this is electron volt and this is volt, but it is only equal 1 for this reaction because lithium is +1. So they are in good agreement. So in this way, of course, in this case, or also in the other cases, experimentally it is known. So probably it is not necessary to predict something. But if it is not known by experiment, or if you predict some new material, only by theoretical calculation you can estimate the battery voltage. So which is quite useful, especially in the field of the discovery. As I mentioned, this type of data is registered in many different kinds of databases. Well, I'm not involved in this project, but this is very well made, so I introduced this result. You can quickly check the project, just typing this project all, and you can find this type of information. For example, if you pat TIO and click the phase diagram, you can immediately produce this type of diagram, which shows convex hull of the formation of the titanium action system. The horizontal axis is a fraction from 0 to 1. So here is TiO2 because the fraction is 0.66. This is TiO, so the fraction is 0.5. Here is titanium metal, here is O2 as a standard state. Probably the pointer is very small, so it's difficult to see, but there's some other point you can see. They are different, the same chemistry, but different composition, same composition, but different structures. So among many different structures, one of the structures have the lowest energy, and it is located on the convex hull. So it means those PS6 or 3 or those are on the convex hull. It means thermodynamically stable. But other compression, something like TI8O, are not on the convex hull, so it is not stable. I will explain that also afterwards. But anyway, this type of information is available. And for TIO, for example, if you click TIO here, there are a number of structures you can obtain. I'm sorry that the characters are so small, but all details are not necessary to be seen. One of the lowest energy structure is hexagonal. Some of you may know that TIO forms as a Roxal structure, but the lowest energy structure by calculation is not Roxal, but hexagonal structure. The food structure can also be drawn within the database. It looks like this one. And they have all lattice parameters, atomic position, etc. The reason why this is the lowest structure and not the Roxal structure is not clearly known. But I can guess that rock structures is more easily formed. And the hexagonal structure, although this is the lowest energy structures, it is kinetically forbidden to have this type of structure. You need very detailed, very careful experiment to obtain this material. It is quite often we encounter, I will show some example for the metallic titanium in the second part of my talk. Why in the case of titanium, the lowest energy structure is so-called omega structure, which you do not find normally. Normally we find HCP structure for titanium. It is also kinetically forbidden to have omega structure in titanium. This may be similar. Titanium, this structure is probably kinetically forbidden. And also for this material, they also have this type of electric structure by structure. This shows good conduction. Okay, first principles calculation can provide that type of structure information, electronic structure, and also here is a force on each atom. Using that force, we can simulate some of the motion of atoms at finite temperature, which is often used for the molecular dynamics calculation. Probably some of you know that molecular dynamics calculation is quite useful to simulate the finite temperature atomic motion. I showed an example for the ionic diffusion in this bismuth oxide. Bismuth oxide is a good ionic conductor because this red one is the oxygen and this is the oxygen vacancy. This violet is bismuth. Because there is a systematic presence of oxygen vacancy, oxygen can go through this lattice quite rapidly. As a matter of fact, this is an Arrhenius plot of the ionic conductivity versus inverse temperature. And at temperatures very close to liquid, in this temperature range, delta bismuth 2 or 3, this shows very high ionic conductivity, close to 1 Siemens per centimeter, which is very high, is very close to liquid. Quite often for the fuel cell, oxide ion fuel cell, the zirconia doped with yttrium are often used for the ionic conductors. But the bismuth oxide is 2 order one higher ionic conductivity. So we simulated this one by first principles of molecular dynamic equation. By simple estimate of the conductivity here using Einstein relationship with this conductivity and also the lattice parameter or bond length here, we can estimate the time required for this jump is something like 15 picosecond at the 1100 Kelvin. So of course we need to longer calculation than 15 picosecond. Of course 15 picosecond in our real time is very, very short. But for the quantum mechanical calculation is quite time consuming. But it is a doable calculation. What we have done is a fast code using NBT constant ensemble and 80 atom cubic cell at this temperature. The time step was 2 femtosecond. So femto, pico, nano is different in 3 orders of magnitude. And to the femtosecond performed this amount up to 1 nanosecond. So this is mean square displacement by first principles molecular dynamic calculation for bismuth and oxygen. You can see that only oxygen shows almost linear increase in mean square displacement like that. Bismuth doesn't move around. Bismuth showed some kind of thermal vibration, but bismuth cannot move around. But oxygen can move around, and from this slope, we can estimate the diffusivity. So this is a diffusion question for diffusivity with time. And it is almost converged at around 500 picosecond at the diffusivity of 1 to 10 to minus 9 square meter per second. By experiment, it was 0.9 by 10 to minus 9. So again, you can find that the agreement between the experiment and the theoretical calculation is quite nice. Also, we can get some information for the diffusion trajectory or how oxygen are moving within this crystal. This is a detailed examination of bismuth 3 crystals, and oxygen are typically located in the center of this bismuth site. but there are another empty 32F site located like that forming tetrahedron. Actually, the oxygen is moving around within this 32F site, not the other direction, but it is moving around within this triangle, tetrahedron. This is a result which shows that type of movement. If you cut this crystal at this 100 plane like this, you can find some of the trajectory of ions like that. And, well, this is so small, so let me expand that. At this height, the oxygen is moving toward that direction. And this side is almost spherical, and this side is going toward that direction. It means the atomic movement are not spherical, it's elliptic movement. So this is quite interesting, and also it was very well confirmed by experiment. The experimenters did very detailed neutron powder diffraction experiment and did a very detailed maximum entropy method analysis to find that the oxygen is actually moving toward this 32F site. So they analyzed the result and also oxygen capacity for the other side and central side, etc. And the agreement with the experiment. So very good agreement. So in that way, the atomic movement, which is very important at high temperature, that type of information can also be obtained by first principles calculation. So we can learn also some other information like the spectroscopy result. If you are interested in infrared or Raman, which we often use for the characterization, it is so-called vibration spectroscopy, and we use the information from the lattice vibration. In I will explain how we compute lattice vibration in the second part of my talk, but here only the results are shown. This is for thin sulfide crystal with different structures. The infrared Raman results are very well reproduced by calculation. So it means if typically IR and Raman are characterized by the fingerprinting technique. If you have some reference material and have some reference spectra, and some of the material you synthesize are fit with this fingerprint, it is that material. In that way, infrared Raman have been used. But now we can obtain a fingerprint by theoretical calculation. So you do not need a reference material prior to your experiment. This is useful. This is also true for the X-ray absorption unit structure. I'm limited, so I will not go into detail, but this is often obtained by synchrotron experiment and the X-ray absorption unit structure, especially this X-ray absorption unit structure is quite useful for the to get the local information of not by the space. It's the same. And also by using PEM, the modern PEM is quite often equipped with spectroscope, the electron spectroscopy, and it can obtain information for the electron energy loss spectrum. It is similar information to X-ray absorption structure. So this is also first principles calculation is also. And another technique quite often used is magnetic angle spinning, NMR. And NMR was also used as a fingerprinting technique with a different material to the but first principle calculation can compute these fingerprint identification. So in this way, well, this is concluding remarks of the first part of my lecture. The first principle calculation is very useful not only for fundamental issues of solid-state physics and chemistry, but also useful for material science issues. It provides systematic material data, which is atomic structure today as well, and structures, energy, physical properties, are useful for data-centric studies. So this is the message of my first group. And well, this is a 50 minutes slot. And if there is some question from the audience, I'm happy to